Okay, so please go ahead, Ryan, for the introduction.
All right. Hi, everyone. It's my great pleasure here to welcome Andrew Selleck to Virginia and remotely at Chalmers. I first met Andrew back in 2022 when he visited University of Arizona. And since then, our paths have crossed at various DISC meetings over the years. Andrew received his bachelor's, master's, and PhD all from Cambridge, where for his PhD, he worked with Captain Clark on protoplanetary disks. Andrew now currently works at Leiden, and he's an expert at understanding disk evolution. And today he'll be telling us about how the evolution of protoplanetary disks impacts the chemistry of their inner regions. So that being said, feel free to take it away.
Yeah, thank you. Thank you, Ryan, for the introduction and for hosting me here for a couple of days. It's great to have a chance to come along and tell you about all the science that we're doing in Leiden and as well in the wider Minds collaboration. So I'll also try and show some of the results from a couple of the PhD students in Irina's group, Marissa and Milou. We're all part of Irina's ERC program, which is called MOLDISC, which is slightly hidden by this Zoom thing in the corner. So yeah, as Ryan said, I want to talk today about the inner disk chemistry in protoplanetary disks and how some of the evolutionary processes going on in the disk influence that. It's always the thing of the first time. There we go. So kind of why are we interested in this? Well, I understand here that within origins spanning kind of all stages of star and planet formation, really from the clouds all through to the planetary systems. And what we want to understand is sort of how the chemistry ultimately of those planetary systems, like the ones in our own solar system, our own Earth, and all the ones that we can now study around other stars, is being set. And the kind of last stage before that is the protoplanetary disk, where you have debris disks and things kind of in between. And then you have all of these different stages of the protostellar collapse in the cloud. And we want to understand, when in this cycle is the chemistry set and how. And so we want to kind of zoom in on the disk and understand what's going on there, and actually also whether we can use some of the information about the chemistry to tell us how the planets formed in the first place. So what James Webb can do, the James Webb Space Telescope, is to zoom in on the inner parts of the disk in the near and mid-infrared. So we're talking the inner few astronomical units where the material gets hot enough to emit these kind of wavelengths, whereas, say, the ALMA array is much better in the outer disk at chasing things there. So that's why I'm going to focus on the inner disk today, because it's really what is being attained at the moment in unprecedented detail with James Webb. Now, the other half of the title was, of course, about the evolution of disks, and they are actually very, very dynamic places. So the kind of basic thing that these are thought of is accretion disks. So we can see from UV excess and various emission lines, there's accretion of material onto the star, and by implication, through the disk. We don't fully understand what drives that accretion, whether it's some kind of viscous turbulence or whether it's some kind of...
Sorry to interrupt. We need you to share screen.
Oh,
it says online that you aren't sharing. Is that the case?
No, you are sharing, so I think it's okay. So that must be a mistake.
Okay. Check your tabs, whoever that was. And I'm sorry to interrupt, Andrew.
No, that's all right.
Continue that train of thought.
So we don't know fully if the accretion is driven by some kind of what we call viscosity, some kind of angular momentum transport within the disk, often assumed to be turbulent, or whether it's kind of extracted by a wind. But we know that the disks do seem to accrete. So I mentioned winds. We have lots of ways that material can leave the surface of the wind. Various people here, including Ryan, one of our mutual interests, work on this external photoevaporation idea. So that if you have a nearby OMB type star, it can remove material from the outer disk. This will cause it to truncate. But even if that's not the case, the central star is a good source of UV and X-ray radiation to heat the upper layers. And so we'll have processes such as internal photoevaporation, which can occur. It's something that I really focused on in my PhD, as well as the possibility of having magnetically driven winds, which are the ones that can remove angular momentum. But one of the key things I'm going to talk about today is going to be more about some of the dust processes, because really when you have dust and gas undergoing different processes, that's how we can get a lot of interesting variations in the chemistry. So we have these processes such as dust, radial drift, and trapping. So that's where I'll focus today. Focus back on that. So what do I mean by this radial drift? Well, when we have a protoplanetary disk, we have the gas orbiting the star, but it's not actually going in a perfect Keplerian orbit because there is some pressure support from the fact that the gas is denser and hotter nearer to the star. And I always like to think of it as kind of these marble funnels that if you have all of these dust grains going round and round, eventually they kind of all fall into the middle because of the friction they feel from the funnel. And the same happens with the dust because it doesn't feel that pressure support. It goes a bit faster than the gas, and this causes a drag force, and that torque makes it all move kind of inwards and causes the dust disk to shrink over time. So it's an analogy I quite like, so that the video is a bit jumpy over Zoom. But you can also imagine that if I put in some kind of barrier somewhere in the disk, I could stop that. And since this is driven by the fact that the gas feels a pressure gradient, we want that to be, say, a pressure maximum so that there is no gradient there. So this is what we might call a pressure bump. So these are some plots of the surface density of the gas in solid and the dust in the dashed lines in some disk models. And you can see what we can do is if we introduce just a little dip in the gas somewhere, just outside of it, we'll have some maximum in the density, and modulo some slight offset because of the temperature gradient, we'll get a maximum in the pressure there. And so what this means is if I start with a pretty smooth distribution of dust, which is a kind of blue line underlying somewhere here, and I evolve it forward in time, pretty quickly, a lot of this dust will get trapped in this pressure maximum. I'll show you what that looks like in a minute, observationally. The other key fact is that all of this dust, as I mentioned before, is moving inwards. So of course, if it starts in the outer disk, it gets trapped here. But if it starts somewhere inside of that, it can move kind of unimpeded towards the star. Now, don't worry too much at this point about these different scenarios that are labeled here. Perhaps there's just one thing to notice that this one that's called scenario 1 has a very different feature in the dust in the inner part of the disk. And that's because in this scenario, it's been assumed that the grains are more fragile when they lose their ices inside the water snow line, which is somewhere about here in this model. And so this causes them to actually stop drifting as fast because they become so small that they just move with the gas. It's known as a traffic jam because they're drifting in fast from here and then they slow down and couple to the gas. And so they build up and pile up. As this will become important later, so I just wanted to point out now that depending on what we assume about the dust, we can get scenarios like this or where the dust distribution is smoother.
The assumption is they kind of fall apart into monomers and they're changing their size distribution when the water dissolves, or what is these?
Yes, so this goes back to the idea that the fragmentation velocity of the grains depends on their composition.
Interesting.
So if you have icy grains, historically it was assumed you could get them to about 10 meters per second, smashing them into one another before they would fragment. And if you have bare grains,
fragmentation argument rather than a like centering ice.
Yes, it's in that case. Of course, that could also be something that would produce a similar effect, but in these models, it's been assumed from the fragmentation velocity, so that the silicates are just more fragile, and so that means that when you smash them together, they break up more easily, and so you can't grow them to such large sizes, and so dynamically they just couple to the gas more. You know, it's easier to blow sand around in the wind than it is to blow a boulder. So anyway, these are the sorts of models that I'm going to use to describe or to explore some of these processes in this talk. So what are these? These are 1D disk evolution models, so they're vertically integrated and just taken as a function of radius. And we solve the gas evolution, assuming it's viscous gas motions. And then the dust radial drift is using the 2 population model. And then we also attach a bunch of kind of molecular tags to the dust grains. And when they cross snow lines, they're able to freeze out or desorb depending on which direction they're going in. And so we kind of solve for this balance of freeze out and desorption. So what happens when you have one of these dust traps? Well, you get something that looks like this. This is a high resolution gallery of the Lupus star forming region from Osmar Alvarado, one of Ninka van der Marel's students in Leiden. This is at something like 4 AU resolution. So you see we have all of these large, very bright disks, many of which show these rings. We also have all of these kind of compact featureless things, and these are typically assumed that they must have kind of undergone unimpeded radial drift. Although to actually prove that, one also needs to be able to measure the size of the disk in gas to show that there is material far out in the first place. But nevertheless, it seems that substructures are more common in very large disks as a sort of effect of the substructures helping keep them large. So that's one, what this manifests as observationally. So pivoting now back to the chemistry, what have we actually started to find with JWST? So I'll show here some of the results from the MINDS collaboration, which is the GTO MIRI survey on mostly on protoplanetary disks. There's a few debris disks and things in there as well. Many of similar things also being explored by, say, JDisks in the US as well as other teams. But I focused on showing some MINDS results here, because otherwise showing every spectrum would be getting very busy. So on the one hand, we sometimes have water-dominated spectra. So these show these kind of dense forest of lines, which are all of these spikes here. It's basically mostly water lines. And what we do with one of these spectra, each of these spectra, we decompose it using slab models, which have a temperature and area, column density to predict the line strengths. And you can see that then when we plot each of these models here, say in blue, this is the contribution from water. So you can see it's really accounting for most of those lines. The pink, I think, is OH, which is counting for a few little clusters here and there. We often have these green triangular peaks from the CO2, for example. But these are two cases which seem to be predominantly water from Danny Hassman's paper and Emilio Temming's paper here. On the other hand, actually, the first disk that MINDS published was GW Loop, which is looks a bit different. The most prominent feature is actually that big triangular CO2 Q branch here at 15 microns. And this is another one which looks very similar, CX tau, that Marissa published quite recently. And actually, what's nice in some of these is we also see the isotopologues of 13 CO2. I think this one here is also the CO18O. There's even one disk in the XUE10 program where they've seen CO17O. So in some of these, we get these really, really prominent CO2 as well as its isotopologues. But even just looking at the water spectra, we see a lot of variation. So here's CX tau and DN tau, two of the compact disks in the MINDS program. And they have fairly featureless spectra, but they do show some water emission, as you saw, particularly around this about 24 micron region here. There's this little cluster. Then we have the kind of ones like DR tau, these really kind of water-rich things with these huge line forests everywhere. But there's also some which show these really, really prominent, even more than in these 24 micron lines. So even just visually, there's quite a lot of variation within these spectra. And this is something that people have explored. And one of the hypotheses that has been put forward is that this is all about drift, which is one of the reasons we start to get interested in these processes. So this is something that Andrea Banzatti has been really pushing, and Carlos Romero Mirza has published this analysis of 7 of the JDisks disks, where these are the compact ones and these are the extended ones, and the hot and colder components of the water are shown here in 2 different colors. And there's this trend in the cold lines where the more compact disks seem to show more cold water. But we can see even just looking at the compact disks here, they can actually be quite varied, because all of these were selected from the MINDS sample to be compact. And actually, if we plot them on one of the same diagnostic diagrams that Andrea did, this is in Milou's paper, which just came out a couple of weeks ago, most of the JDisks ones have appeared down here, where the more extended ones are a bit more towards the bottom, the more compact ones are a bit more up here. But actually, within our compact disks, we're also spanning a very large range of parameter space. And so what Milou tried was just fitting various functional forms to the kind of distribution of water in terms of how much the column density you would need at each temperature to try and explain the spectrum. And one thing you can try is just a simple power law, but then we can try different features on that, having an exponential tail that kind of cuts it off, or maybe having some jump somewhere that represents an enhancement. And we definitely don't have the confidence to say, oh, this sort of profile is better than this one on the whole, because a lot of the time you can reasonably capture the similar behaviors with different ones here. But what we can see is that between the different types, these are the type the P, as we call them, the ones that are quite poor in their water, and the type N, which are the ones that kind of called them normal, and then the type E, which are the ones that are sort of up here, where they really have this enhanced cold water. And looking at these distributions, we see that depending on the type, the fits come out in a similar way. And it's telling us something about that. For example, in the type E, it's really enhanced in the cold water. And if we try and fit, say, a parabola, it's got this upwards tick. If we fit this column density, it has this jump towards the cold water here. So these are the sorts of things we want to try and explain with disk modeling. But it's definitely looking a little more complex. One of the other key results has been that if we look at these disks as a function of stellar mass, there's a real change once you get below about 0.2, 0.3 solar masses. And the disks then become nearly always very hydrocarbon rich. There's one or two notable exceptions. But again, these are the 10 disks from mines, plus I think we accreted one from somewhere else. And this is the table of hydrocarbon detections in particular, as well as a few other things. And we're seeing all of these things, C4H2, C6H6, even sometimes C2H4, C2H6, loads and loads of hydrocarbons, which are very, very rarely detected, most of these around the solar type stars. Mostly around the solar type stars, we'll see maybe C2H2, a couple of tentative detections of CH4, but not a lot else in terms of most of these. And it's actually quite nice to just scroll along this spectrum here, because really all of these features are actually being attributed to hydrocarbons. This is the video made for the IC147 disk in Aditya Arabhavi's paper and science on it. And now this is the overview of the mine's low mass stars, which Aditya just published as well. So we can see all of these features. Give it a moment to play through. Interestingly, there does still seem to be some kind of divisions in here, that some of these seem to show all these C2HN hydrocarbons and others don't. So there's still some variation amongst this class, but yeah, most of them are very hydrocarbon rich. So what does that mean? Well, what people are finding with thermochemical disk models is that if your CO/O ratio is somewhere below 1, most of the carbon gets locked up in oxygen-bearing molecules like CO2. And so you do get some hydrocarbons, but they're fairly limited in where they're going to appear in the disk. Whereas if you go to a CO/O ratio of greater than 1, we now have these kind of abundant areas of lots of these hydrocarbons right up in the disk surface where they'll be visible to us, where the gas is hot enough and simply not extincted enough by the dust in the disk that we'll see them. So this is something very interesting, that it looks like these disks are more carbon rich, which is something we might want to explain. And indeed, there's also tentative trends that there's an age dependence here. So this was the paper by Feng Long, looking at this very, very old disk, but comparing it to a few others and saying it seems to be even more carbon rich when this was derived from the CO2 to C2H2 column density ratio. Even if we just kind of sticks to the fluxes, which involve a bit less interpretation and putting absolute numbers on, it still seems that the older regions seem to have less CO2 with respect to the C2H2, or indeed the same in the isotopologues, which could imply, therefore, that they are more carbon rich, even if you are skeptical about the absolute numerical scale here. And the key thing is, I mean, some of these numbers that are being predicted are not just slightly more than 1, they're really 2 or 3. So you really have quite a lot of excess carbon over the oxygen compared to the solar value, which would be about 0.5. So you have to find quite a lot of carbon from somewhere or get rid of quite a lot of oxygen. So what's responsible? Well, can it be chemistry? Well, that really conserves atoms at a given location. So if you just have a completely static disk, you can move the atoms between different molecules, but you can't actually change the C/O ratio. On the other hand, transport will redistribute the atoms according to the volatility of the molecules that they find themselves in. And so if your oxygen-bearing molecules, it seems, are actually generally less volatile than the major carbon-bearing molecules, this will actually allow you to produce variations in the CO/O ratio. So there's 2 scenarios then that we want to explore in all this. One is that scenario I just mentioned, where you have some physical and chemical evolution of the disk. The other scenario that I should mention that's also been put forward to explain all this extra carbon is that you get it out of a refractory source of carbon. So if you can take the dust grains that contain carbon and somehow get that carbon out by eroding the grains, perhaps in the inner disk where it's particularly hot, that can be the extra source of carbon. So that's something that other groups are working quite a bit on. There was a paper just out last week when I was on vacation, so I haven't yet had a chance to see everything that they say about it. But that's one hypothesis. This is the other hypothesis, and we want to explore which of these is more likely to explain this variation in kind of carbon and oxygen chemistry. So how does this all work? Well, in a protoplanetary disk, you have the star heating up the disk, and so you tend to have hotter temperatures close to the star and colder temperatures further away. And if you then start to consider the balance of the thermal desorption of the molecules from the warm dust grains with their absorption to the dust grains if they collide with them, you find that if you have something like CO, it actually tends to desorb at about 20 Kelvin. i.e. pretty far away from the star, you can already get it into the gas phase. If you then take something like CO2, it's a bit harder to sublimate, and so it's comes into the gas phase a bit closer to the star, and water even closer. And so these locations are known as snow lines, or sometimes ice lags or frost lines. People use these quite interchangeably, so I tend to use snow line for no particular reason. But we tend to have this pattern, therefore, where if you're somewhere out here, you have really only CO as a source of these molecules in the gas phase. Once you're in here, you have all of these extra things as well, so you're going to have more oxygen. And the next thing that can happen is that if I now consider a dust grain in the outer disk and I let it move forward, it's going to desorb all its CO ice at the CO snow line, CO2 ice at the CO2 snow line, and the H2O ice at the water snow line, at least assuming that there's not really efficient trapping of one molecule within another, which can occur. And so it could shift some of this inwards, but it will at least leave some of its CO2 here, some of its CO here. So now I have these enhancements of these molecules at certain places in the disk. I.e., each molecule is essentially deposited at its snow line. And now if I wind the clock forward and the gas evolution, we'll see that each of these slowly start to spread towards the inner disk. And if we track the amount of mass that's in the vapor, we see that we start to have a peak in the water early on, then the CO2 is going to come in and we'll have CO2-rich things, and then finally the CO and other things like CH4 come in, and we'll get something else here. Problem is, at these very late times, actually no, I'll come back to that in a moment. So how does this look if we just sort of plot the abundances of C over H and O over H against one another? Or we can say what's the C over O ratio as a function of time. I'll play this a couple of times so you don't have to try and watch 4 panels all at once. But we can start the disk somewhere here, which is at its solar composition. And if we start the clock running, you see things initially move to the right. So this is as the water is delivered by the drifting dust grains. It then starts to move up, which is as the CO2 starts to come in, but it's also already bending to the left as the water's getting accreted, and so you're losing a lot of the oxygen. And then it eventually kind of hits this line, and it sticks very, very carefully along this line in terms of this is where the C over H and O over H are equal. I'll try and play that again. You see, first you enhance the oxygen, and actually what that does is that will decrease the C over O ratio in the bottom panels. And then as the CO2 starts to come in, things increase again. And then when it's hitting this line, it's really tending towards the point where C over O is greater than 1, but it's not crossing it in any of these models. And that's because one of the most abundant molecules in disks is CO, which has a CO2O ratio of 1. So if you have abundant CO in the model, it will get basically stuck at this line, and we never produce anything kind of above this line where we expect that the very low mass stars might like to be. So although the very low mass stars, if you look carefully, they go through this sequence faster. They reach in about 2 to 3 million years C over 1 compared to the solar type stars on the left, which take 10 million years to reach it. They still don't actually cross it. So they might have higher C over O, but it's quite hard to get them over 1 in this case. So what's the problem? Well, actually, one thing we know is that the outer disk is not necessarily always abundant as in CO, as we might assume. So in the ISM, we typically find that it's about 10 to the minus 4 with respect to hydrogen. However, if you look at the luminosities of the CO lines and isotopologues and compare that to the luminosities of the dust that we see for protoplanetary disks, we find that they're much lower than we would expect for a typical dust-to-gas ratio. One way of explaining that is to say that, well, we have to just make the gas to dust ratio about 1. So we've removed a lot of gas and got a lot of dust left over. But that's kind of counter to what we expect, for example, from radial drift, which tends to remove the dust much quicker than it removes the gas. The other thing is to say that, well, perhaps the carbon and the oxygen are just depleted by some factor, somewhere between 10 and 100, which allows us to keep the same amount of dust, keep the same amount of gas, but just lower the particular molecule that we're looking at. And this has often been the favored explanation. And so there's even some suggestion then that if you start to take these very, very young class 1 disks, we do see still ISM levels of CO. But once you get to the class 2 phase, we sometimes see 1 to 2 orders of magnitude of depletion of it. And when I say depletion, I have to be very careful because Irina is always very, very specific about what she means by this. If anybody's ever talked about this with her, it's the fact that CO is underabundant on top of what we expect from freeze out and photodissociation, which is included in these kind of models. So it has to have been, not just frozen out or just photodissociated, but it really has to have been transformed into something else, perhaps in some grain chemistry, or it really has to be physically removed to somewhere else in the disk from where we expect it. So these are some models then from Sebastian Kite following the work by Atop, which undergo some chemical modeling coupled with physical modeling to try and explain this. So here they have the CO over NH ratio in the gas, here in green, about 10 to the -4 at the early times. But after 1 million years or 3 million years, it's really been reprocessed in these upper layers, the CO, into other things, which has led to this depletion, apparent depletion of CO. And if we look down here, what are the main culprits? Well, where it's kind of comfortably frozen out, we have lots of methanol forming. Where it was kind of in the upper layers in the gas phase still, we've had a lot of methane forming. So these models, they're kind of a toy chemical network really, but they're based on more detailed chemical modeling by Atop, which suggests that there's 3 main routes, 2 in the ice phase to methanol and CO2, and then 1 in the gas phase to CH4 and hydrocarbons. So what we tried to do was simplify this even further to incorporate into a simple way in our 1D models. So I won't go through all of this in detail, but here are those 3 pathways. So CO in the gas phase, it interacts with helium ions to turn into methane. In the solid phase, it can either be hydrogenated to methanol or connect with OH to CO2. But note that both of these things are radicals, so they still need something to be broken up. So actually, all of these things require some input of normally, say, cosmic rays or ionization that can produce either the direct ionization or the UV photons as a secondary effect of that can break up the kind of obvious parent molecules of these so that you then have some reactive species. But note, if I would just turn this into methanol, I turn this into CO2, I still have a bunch of oxygen hanging around. So if I move this molecule around in my disk, I'm not really going to solve my problem because I'm bringing as much, if not more, oxygen. So the really key one actually that we're going to be interested in here is this one here in the gas phase, because this is actually what allows you to, this is a process which actually breaks that CO bond and actually liberates the C, because that's what we need to do. We need to be able to raise the C with respect to the O. So where would the oxygen go? Well, most likely it would say react with some hydrogen, end up in water. And now this is a much more volatile molecule than this. And so this is likely to freeze out onto a dust grain, drift rapidly through the disk, whereas this is likely to remain in the gas. And we have a mechanism for sorting into that. There is one other thing on here which breaks the CO bond, and that is you can photodissociate the methanol ices. The branching ratios of this are a bit uncertain, but I will show a model where it becomes important towards the end. So what happens now if we go back to our plane of carbon abundance versus oxygen abundance, or CO ratio over time, and press play on the evolution? So actually, if I start it for a moment. Here I'm now looking at a grid of models of different initial disk sizes, as well as different ionization rates. So in the green, we have the kind of fiducial one that's often assumed of 10 to the -17. But then we have an elevated rate in the kind of orangey brown colors and a depleted rate in the blue colors.
To clarify, are these mid-plane ionization rates?
Incident on the disk.
Okay. And so there's some attenuation factor?
Yes.
Sigma.
Yep.
Okay.
Yep. That will be on the next slide. Oh. But yeah, So if I play these, the same thing happens initially, that you move to the right as the water comes in. There's still that abundant water. You move up as the CO2 starts to come in. But now, once you start getting to the sort of million-year timescales, you get models that do cross the line because you've removed a bunch of the CO into other things, particularly the methane. And so I get things that are in this sort of upper left triangle on the here, or cross this line now. So that's great. Is the problem solved? Well, maybe. What we then have to ask,
It's the oxygen that's getting removed.
so yes, so
Methanol.
we break up the CO.
Okay.
In this case, this carbon ends up in methane, the oxygen is ending up in water. then you have efficient radial drift that removes that water from the disk. So yeah, it's really a scenario where you're doing this, you're destroying the CO, so you get the apparent CO depletion, but you're actually doing it mostly by removing the oxygen. Although if you can say if the CH4 goes on further reactions, C2H2 and things, you do get, you do have by the end of these quite significantly depleted carbon in the inner disk as well. So what conditions were favorable there? Well, if we start by remembering actually that on the solar mass stars, we don't tend to see all these abundant hydrocarbons. We probably want the CO ratio to remain for most disks below 1. What I've plotted here is a function of the ionization rate and the initial disk size. In the inner ring, the maximum CO ratio reached in the first 5 million years, in the outer ring, 10 million years. So most of our observations are the first few million years, so we'll just focus on the inner ring, and we want these to remain below 1, so we want the purple models. So we want something like this, something below about the kind of fiducial rate, which is great, that's fine. But the very low mass stars, it's kind of the opposite. We really want to be green in the first few million years because we're seeing lots of disks with high CO ratio. So we kind of want them to be to the right here. We want them to have ionization rates of at least the kind of fiducial 10 to the minus 17 in order to get this to work. So then what did we put into the models? Well, yeah, this was the incident rate in a model where I say it's 10 to the minus 17. And then this is the rate that I'm plotting here is the rate at the midplane. So I have some attenuation. I've then put in a floor from SLRs. And so in the outer disk, it's kind of transparent enough even to the cosmic rays that you still get the kind of incident rates. But in the inner disk, it becomes highly attenuated. And so you don't have much of the chemistry going on there.
But the SLRs aren't changing in time, they're flat.
Yeah, in this case, I've assumed it as a static floor, basically because this level was low enough to not affect it anyway. And otherwise, then I'd have to start also working out how it coupled to the dust abundance. So it was just a simple way of having some floor. It could also, and I did this at about the maximum rate achievable by SLRs. Of course, it could also come from something else like X-rays or stellar energetic particles or something like that. At the end of the day, this is just a number that goes in to determine the rates in the pseudo network. It's not actually physically derived from anywhere. So what do we see in the observations? Well, actually, most of these constraints are from Ilse and her group, and they tend to not be more than about 10 to the minus 18. I think I always struggle a little bit to fully understand if these are mid-plane or incident rates, depending on whose model you're looking at.
They're incident.
They're incident.
They're
Okay. Yeah. So, in that case, well, we've assumed something higher, but that's fine. We wanted these to be no higher than that. So if we have that incident rate, it's fine. It's not going to drive very efficient chemistry, but at least for this problem in particular, we don't need it to. On the other hand, for the very low mass stars, we kind of need it to be at that 10 to the minus 17 rate. Now, unless I'm mistaken, I don't know of any actual measurement for a star of, say, 0.1, 0.2 solar masses of that ionization rate with ALMA. So to me, that's an open question of whether that could explain it. We either need to have some local production that gets it. We say we have the same incident rate, which is decreased from the kind of standard because of the ion exclusion, and we need to either top it back up again with something local, or we would need to have less exclusion, which maybe could be possible. So that's something that I think needs exploring further in the future to understand whether we do have the conditions to drive kind of efficient chemistry around the very low mass stars. One way we could try and test this, though, observationally, is to try and compare the inner and outer disk abundances, because in this case, everything we're seeing is because of the chemical evolution of the outer disk and that gas then being brought in. Now, this is something which is definitely being done for the disks around T-Tauri stars. I think from what I saw in Ilse's talk in Leiden on Thursday, the first hints are that the inner disks as an ensemble have lower CO ratio than the outer disks. But this is something we also perhaps need to do for the very low mass stars. And at the moment, the MIRI and ALMA samples don't overlap very well. So on one side or the other, we need to try and plug that gap. But what we should expect to see, because this processing happens first in the outer disk, is if we compare the inner disk on the y-axis with the outer disk on the x-axis, first of all, you should raise the CO ratio in the outer disk, and then that should be transported to the inner disk. So you should kind of move right and up on this plot, and generally remain below this diagonal line. On the other hand, if you were destroying grains in the inner disk, you would expect that to first affect the inner disk, the hottest parts, and then maybe that carbon enriched gas can spread outwards. And so maybe you'd go up and right, and you'd end up somewhere above this line. So I think these kind of comparisons would be kind of critical to understanding whether this sort of explanation plays a role here. Now, what about the dust traps that I mentioned before? Well, what they will do is you have essentially normally a grain growth front, which grows outwards through the disk, spreads outwards through the disk, and then the dust grains start to come in. If you introduce a trap somewhere, and let's, for the sake of argument, we'll put it in at t equals 0, once that grain front reaches the trap, basically no more grains are getting into the inner disk. So you cut off suddenly the supply of your pebbles, your drifting dust grains. And so, whereas when you had no traps, you would see these increases in the vapor, masses in water on the right and CO2 on the left, followed by a decrease as that gas then accretes onto the star. If you introduce a gap, you just cut off the top of that peak. It happens a little bit earlier. It happens a little bit not as high. But what's quite interesting is that the water shows a much more sudden drop than the CO2. And that's because that snow line is closer to the star. So all of that water vapor can accrete onto the star on a kind of viscous timescale at the snow line, which is quite short. Whereas if you're at the CO2 snow line, that's a factor few further away. So it takes a factor few longer to actually accrete all of that gas onto the star. So the fact that the water reacts more quickly, I'll come back to in a moment, but there's something else to consider as well in terms of what we would actually see. And that's that drift delivers dust as well as molecules. And we've been thinking only about the molecules here. But if you remember this scenario 1, I said that the dust grains actually stopped drifting when they came inside the snow line and coupled with the gas. And then that means for every molecule that you've desorbed, that dust grain is still there. And it's actually providing a source of opacity, continuum opacity to the disk. So if we assume that the visible column that we can actually see is essentially the total column above the tau equals 1 surface, which for large optical depth is just about 1 tau, is the fraction, then we find that the column that we're going to see is actually a kind of fixed number that's just sensitive to the water to dust ratio, but that's not changing if the dust couples to the gas. So in that scenario 1, we have this kind of insensitivity to the actual true amount of water here. So this is something we pointed out in my recent paper. It's also been pointed out by another group, of Sebastian Kreit's group, with a paper led by Adrian Huge. What we also pointed out there was the CO2, because it's coming from a bit further out in the disk, it remains a bit more sensitive to this. So it does see some patterns where, as you bring in the dust, it kind of skew it, but then also, as that dust becomes less optically thick, you start to see more of it. And then eventually you're kind of tracking 1-to-1 somewhere here. So, yeah, getting towards the end, I think, so that's good. So this leads to two key things. First of all, as we saw before, the fact that the water reacts faster to the loss of supply of pebbles and the drifting dust grains than the CO2 means that if we had the smooth disk model in kind of hidden under here in grey, if we put in the gaps, we tend to amplify the CO2 to water ratio because the water disappears more quickly, and whereas the CO2 hangs around for longer, and so it pushes this up. The second thing is that actually taking the ratio kind of cancels out a lot of those horrible dust attenuation uncertainties. And so we see that the column density ratio that we get from here more accurately kind of tracks the vapor mass ratio. There's a pretty good qualitative comparison between the two plots here. Now, if you're interested in how I get these column density ratios, ask me afterwards. But we can then see in these plots either left or right the same features. So we have these kind of low CO2 to water disks, which are the ones where you're still in this water dominated phase, in this snapshot from the cartoon I showed, animation I showed earlier. And at the peak, you're in this kind of CO2 dominated inner disk phase. It's worth though interrogating it with 2D models whether this is what we actually find. So Marissa Flusblom has just submitted a paper doing some of this modeling. So you have, for example, a thermochemical model that predicts the water abundance. We also have some parameterized abundance models, and trying to work out for these, if we take the spectrum and then ask if we do the slab fits to that, what do we get? So doing the kind of retrieval on a thermochemical model, we found at first that actually, yeah, we are actually measuring column densities that are about the column density down to the tau equals 1 surface. That was great. We got, okay, the assumptions that we made in the previous work was kind of justified. Although then when Marissa's increased the dust settling, we're finding that the column densities that we retrieve don't go up anywhere near as much. So of course, at this point, it could be being limited by where the hot gas is. It could be limited by the optical depth of the water. So some of this, might mean that you do have a bit more sensitivity than implied before. The second key thing that was really interesting comparing these models, so here they are again, was that actually they show very different behaviors in that 24 micron cluster of water lines that I showed earlier. So the chemical model is in black, but it's basically peaks about here, 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 and here. So you get a fairly level set of certainly these 3 lines in the middle. And that's seen in some disks like CI tau, which is quite an extended disk, if I remember rightly. On the other hand, this 10 to the minus 4 case, where here, labeled here, so this parameterized case showed these big spikes in the first and third lines in this kind of quartet. And we do see that in some observations as well. So it's telling us something interesting, actually, that about the presence of these lines seems to be really tracing this region above the mid-plane snow line, above the snow surface. And we really need the abundance to be about 10 to the minus 4 in there. If it's already decreased to 10 to the minus 5, you go back to these kind of very flat distributions. So actually, by comparing to the thermochemical models, we're getting some handle on how that water really has to be distributed in 2D, even though the dust grains that are drifting are mainly at the mid-plane and dropping it all off here. We seem to need some mechanism to efficiently get it out above the snow surface there. So I think we need to start thinking about the transport even more in 2D going forward. A final complication on this is whether the traps are leaky. I mentioned that they will block the dust, but in actual fact, they're not 100% efficient at blocking. If you have the small dust grains, they can still get through, for example. And so this was some nice work. So the reference is missing under here, but from MIRI et al., where they varied the depth of the gap. And when you have very, very shallow gaps, it basically has no impact at all. So these are the shallow gaps, and you just get the same evolution. When you go to very, very deep gaps, it really stops the water coming in, and so your water becomes immediately much more depleted, and you get these much more red colors. But there was an intermediate phase of these kind of shallow enough gaps that they block the water, but then they can kind of re-release it over larger timescales. And so then they really extended the water-rich phase. What we found in my work was that if you have a more extended dust trap, it lets more water through in the first place, and so you get, or CO2 in the first place, so you get much more vapor in the disk. But actually at late times, the trend reverses because the ones closer to the star, the assumptions we made, retained more dust, and so they had more dust available if a small fraction of it was leaking to come through. So compared to a disk with no traps, say, you can actually get more vapor sometimes if you have a leaky trap, because otherwise there'd be no dust left in the disk basically at all. Even if it's only letting through a small fraction of having retained a lot of mass can be more than what would be left otherwise. And so we see that here, for example, if I introduce a trap that's deep enough, I'm decreasing both my C over H and O over H abundances in their kind of final position on these tracks, like we saw in the videos before. Something that was interesting, though, was some which actually showed increased C over H. And when we dug into this, these are ones where the dust trap had been placed inside the CH4 snowline, but outside the CH3OH snowline. And then you had all this dust in the dust ring here, which had all this methanol ice. And then because of the assumptions we put in, this methanol ice was actually photodissociating into methane, which was entering the gas phase and was then able to get through. So it's interesting to think as well that if you have these traps close enough in, there could be kind of ice chemistry going on in there that could actually produce more volatile molecules that escape. Yep. And then the final thing I wanted to really mention on the work that our group's been doing is the idea that cavities can also change the appearance of this ratio. If I have a cavity that might have been carved out in the inner disk for some reason. So if I have a model without a cavity, in these thermochemical models that Marissa did, tended to be dominated by water. When you put in a cavity, it becomes dominated by CO2. Other groups have been working on other things. So, for example, internal photoevaporation really stops all of the gas coming through and means you have this opposite effect where the water can actually get recycled at its snow line. And so it's kind of trapped in the inner disk, and that actually lowers C over O. Other groups have been looking at external photoevaporation, basically with the idea that just like the traps block the pebbles from coming in, if you have truncated your disk because of external photoevaporation, that reduces pebble flux coming in suddenly at some point. But they found that at least when they put it in only after 1 million years of the external photoevaporation, it didn't make much difference to the C/O ratio. So it all depends on how long you can shield your disks from that fall. But there's still other things that need to be explored in terms of irradiated disks, I think, in terms of the heating, the dust destruction and things like that. So this is the summary of what we've been finding. There's really diverse chemistry in the inner disk, some C/O, some carbon-rich with high C/O, but even amongst those that aren't, some with rich water and different distributions of how that water seems to be spread in the disk. If we want to get to C/O of greater than 1, we need this extra carbon from somewhere. One place could be to break up all the abundant CO, which otherwise kind of buffers you to CO ratio of 1. And so we really need to compare inner and outer disk C/O to try and test whether that is the explanation or whether it comes from refractory material. And dust traps will have this effect of interrupting the flow of dust. Unless they're kind of really, really significantly leaking, that will tend to accelerate the increase in CO2 over water, or C over equivalently. But the observable manifestation of all this depends on how the sublimated molecules are then transported in 2D to the upper layers, as well as what the dust is doing at the same time, and we shouldn't forget about that. So thank you very much, and I think we have a few minutes for more discussion. Yeah.
Okay, thank you very much. Okay, then, so Ryan, help me with the moderating the discussion. I'll help here. So Andrew, maybe I can ask, I favor the refractory aspect, I think, myself from the soot line, which would predict the temperature of the carbon-rich material is pretty warm, around 500 Kelvin. I guess in your model, it must be at about 100 Kelvin below the water ice, outside the water ice line. So can we not tell the temperature of the gas that is carbon-rich from the data at the moment? And I just confirm your gas would be about 100 Kelvin, whereas from the soot line it'd be around 500 Kelvin.
Yeah, that's a good question. I guess, yes, our carbon-rich molecules would be forming reasonably far out in the disk, where the temperatures would be quite low. They would then over time, of course, be accreted towards the inner disk, and they would eventually reach those hotter regions, which, being hotter, could dominate the spectrum. And most of the time we're fitting one component here, and what we see, for example,
but doesn't the water is also liberated inside the water ice line, so that surely stops the CO ratio going too high.
Well, but in these models, what I'm plotting is I was plotting the C over H and the O over H and the C over O ratio. Unless I was specifically doing the comparison of inner and outer disk, I was always measuring this at the inner edge of my models. So there's a point when enough of the water had been accreted onto the star that had been released from the pebbles, and you are then bringing in the carbon-rich gas that even inside the water snow line, the C over O ratio is greater than.
Right.
So that's the challenge, is to get those conditions. It's not easy to do, especially if you have a lot of CO. And yes, the water doesn't make that any easier. I can perhaps show that actually quickly.
So you don't have a steady supply of pebbles from the outer disk. You have an initial disk which can then deplete its pebbles, and then once most of the water's gone, then you're left with carbon-rich.
Yeah, precisely. So that's what I was showing, that you initially have this abundant water phase, but then you tend to transition into the CO2 phase and potentially into a CO dominated phase. I mean, you can see, and this was one where we didn't include the gap, so we didn't have any of this trapping. And here you can see the CO ratio was a bit more than 1 at a few AU, but then did dip below 1 inside here. So this was one where it wasn't achieved without putting in this gap, which is why it was quite hard to get inside the water snow line. But yes, the key thing is you don't want to keep in the water.
Yes. Well, Ryan, if there are questions there, please take them next.
I have a question, but does anyone else? So one thing I always wonder about these M dwarf stars compared to the solar ones is that they're more X-ray active sometimes. Do you think that could be a factor into why these disks are carbon rich? Because I know you're showing, ionization rates. I wonder if X-rays are contributing more.
Yeah, so
the cosmic rays.
I've thought about this a bit. So the X-rays, they're not generally as penetrating as the cosmic rays, so they're doing more in the upper layers. Now, there's the work from Catherine Walsh doing these thermochemical models of the different masses, and there she had a much higher X-ray to UV ratio around the very low mass stars, which means that the kind of balance of the photochemical processes that can happen is different. And so that is generally favorable to more of the kind of hydrocarbon formation. However, certainly when we go to say main sequence stars, yes, the M dwarfs are fully convective, whereas solar type stars aren't. And so this gives them these really efficient magnetic dynamos. They're really, really X-ray active compared to their bolometric luminosities. They have a high Lx over L bol. On the pre-main sequence, all of these stars are going to be fully convecting still because a lot of them are coming down their Hayashi tracks. And if you look at the surveys from, the Chandra projects in Orion and Taurus in the 2000s, the Lx over L bol is quite flat actually with stellar type. And so if you assume that's constant, your temperature at a given location in the disk, let's say the water snow line or the cirrus snow line, depends basically on your L bol, upon R squared. And of course, the X-ray flux that you're receiving there is Lx upon R squared. So if you actually consider a certain temperature that you want to reach, it ends up working out that they should have pretty similar X-ray fluxes at a given snow line, because the X-ray luminosities of the very low mass stars are actually generally lower than the solar type stars.
So if I could just jump in, because I was going to ask a question specifically about the X-rays, and my feeling is that it is X-rays, it's not the cosmic rays. You mentioned that the X-rays don't go far enough. I am curious, what are you assuming? I have a follow-up, but what are you?
I just mean in terms of the typical energies of.
But how far do they reach? Are there X-rays in these models at all, or is it just cosmic ray driven?
Well, in what I'm showing here, I'm just putting in a ionization rate.
Okay.
And then, what I'm assuming for what's getting to the mid-plane is based on the cosmic ray attenuation length. But X-rays from the stars typically peak at a kilo electron volt, and the cosmic rays are much higher than that.
So most of the energy density, though, that gets into the molecular layer and deeper.
Yes. So those can be, of course, higher. But then it's a very small fraction of the Lx. And I think the models that I've seen from, say, Christian Raab or Donald Rogers, it looked to me like the ionization rates that you get from the X-rays. Well, they could be dominant, but they would be much lower than what we would need here.
We could follow up. We'll meet after this.
Yes.
But I think it is quite viable that this is X-rays, but it might not be the X-ray increase in X-ray luminosity that creates a low mass stars, different hydrocarbon rich chemistry, but it's also known, right, that these lower mass stars have this higher drift, or the dust evolution is more advanced, and X-ray capacity is set both by gas and dust.
Certainly once you get to those high energies, yes.
Yes.
It'd be great if someone did XMM or Chandra to get
Be cool.
strain.
Well, I mean, a lot of these will have X-ray luminosities, but as I say, the luminosities tend to be lower than the solar type stars in a way that I've never been convinced that you get more X-ray incident flux, shall we say, but maybe the vertical transfer is different.
They might make it into the disk better. Anyway, we can let Sean.
We have another question here, if we may.
Sure.
Yeah, it's from me again. You mentioned, are there systems where you've got James Webb and ALMA? Because again, your model would predict in the outer disk the water is gone, so that that chemistry surely would be quite different than if the water's there. So what's the status of checking with some kind of ALMA prediction from your model?
Yeah, so we haven't done detailed ALMA predictions from these. As far as I'm aware, there's not that many measurements of water with ALMA. There are some, but I think it's a couple at most to look for that directly. I mean, what tends to be done there is to take CO and C2H and then use that to derive CO ratio. I think, to be honest, the largest sample with both JWST and ALMA is probably Ilsa's deco data.
Column in cities that you don't want to go through the trouble of synthetic observations.
Yeah. There's always the balance, because you have to still get from the models to the column density that would be observed. Not the same as the column that's still quite in the midplane, for example, but true.
But you do require the water to be gone from the outer disk, don't you?
Yeah, yeah, certainly. Well, I mean, it would all be frozen out anyway in much of the outer disk, right? Of course, you do have up to about 10 AU. You have the snow surface. Maybe you have a bit of a photo dissociation layer or something. I mean, there's a few Herschel measurements, I think, as well. But I mean,
But I thought you require the water to be, even the ice to be have drifted in already.
Yeah, exactly. But it's quite hard to see that directly, right? If it's in the ice, unless you have some background absorption. But there's not many targets that are ideal for that unless they're edge on.
Well, there may be something to do there. Yeah.
Yeah. Maybe. But I mean, I think in a lot of these disks, we do expect that to have been, radial drift, so we can sort of see that in the dust. So maybe that already tells us what we need to know. But as I say, there are these trends that the ones with less dust in the outer disk, into the fact that they're more compact in their dust distribution, seem to show sometimes more water in the inner disk. But while there is an overall trend, there's a lot of scatter around it. So it could be that, some of the older ones where they have lost that water. But we don't, at least with James Webb at the moment, have particularly large age spread. I mean, it will come cycle 2 observations, but.
Okay, we should wrap up soon, but are there any last questions? Okay, if not, let's thank Andrew again for a great talk and discussion.